It begins with a quiet drift, an invisible force sliding beneath our feet, unnoticed by most, but essential to everything we know. The North Magnetic Pole, once a reliable marker for navigators and compasses, is sprinting toward Siberia. Not drifting, not wobbling. Racing, 40 meters per year. It's a pace so swift that it's overturned models and theories that were once treated as gospel in climate and earth sciences. What once moved in centuries now shifts in months. Pilots, satellites, and submarines all rely on magnetic certainty, and that certainty is vanishing. This script isn't about predictions or panic. It's about a pattern that has become impossible to ignore. Our planet is misbehaving. Or perhaps behaving according to rules we've yet to discover. In recent years, Earth has begun revealing a string of baffling behaviors, environmental anomalies that don't fit our scientific equations or our cultural expectations. They defy logic, disrupt ecosystems, and rewrite the boundaries of climate science, geology, and physics. Yet they are undeniably real. This documentary isn't about sounding an alarm, it's about listening. Listening to the Earth's quiet signals, the subtle pulses and sudden disruptions that hint at a larger story unfolding beneath the surface. Because the data isn't isolated. One anomaly could be dismissed. Two might raise eyebrows. But what happens when 10, 12, or more begin to surface? Across continents, across disciplines, all moving in tandem. You'll hear about rivers in the sky that cross deserts where no ocean touch is possible. About oceans whose currents reverse direction, contradicting the very forces that supposedly drive them. About permafrost that melts and freezes at the same time in the same place. Atmospheric lightning that dances in cloudless skies. Earthquakes that crack open in zones once believed tectonically silent. This isn't science fiction. It's happening now, measured by satellites, confirmed by sensors, recorded by researchers whose findings are often met with discomfort or disbelief. The question isn't whether these events are real, it's what they mean, and what they suggest about the fragile grasp we may have on the systems we thought we understood. For decades, climate science has offered a model of change that is steady and linear, warming trends, sea level rise, glacier retreat. But these anomalies don't follow that pattern. They jump, they surge, they appear and vanish. They are not incremental. They are transformational. And in that transformation, we may be seeing something far more profound. The Earth as a complex, dynamic organism, one capable of sudden shifts, spontaneous reorganizations, and behaviors that feel more alive than mechanical. In the following episodes, we will explore these events one by one. Not to sensationalize, but to bear witness. Each story will begin with a moment, a strange reading, a confused animal, a pulse from the deep. And from there, we'll unravel the human experience behind the data, the pilots who lost their way, the scientists who questioned their instruments, the communities who saw skies rain in places that had never known water. And always we'll return to the bigger questions. What if we've been asking the wrong questions? What if Earth's systems are not linear, but layered and interwoven in ways we've barely begun to grasp? What does it mean to live on a planet whose rhythms we can measure, but not predict? This is the beginning of a journey into the magnetic chaos, the rivers that flow without oceans, the skies that burn without clouds, the Earth that trembles in silence. This is a story of wonder, humility, and the frontier of planetary understanding. And it all starts with the quiet, urgent shift of a magnetic pole racing across the top of the world as if trying to tell us, pay attention. It was the kind of detail only satellite engineers noticed at first, a subtle wobble, an unexpected drift, but over time it became undeniable. Earth's magnetic North Pole, once steadily edging through the Canadian Arctic, began to surge eastward toward Siberia. What used to be a gentle migration of a few meters per year suddenly accelerated to over 40 meters annually. Then 50. There were no clear warnings, no geological tremors, just data, stubborn and strange. Navigation systems began falling out of sync. The World Magnetic Model, which guides everything from smartphone compasses to aircraft autopilots, required emergency updates. Normally adjusted every 5 years, it had to be recalibrated in under 2. Pilots reported discrepancies between onboard instruments and GPS coordinates, especially over northern Canada and Siberia. In a world increasingly dependent on precision, magnetic drift became more than a curiosity. It became a threat. Dr. William Brown, from the British Geological Survey, confessed in a quiet press statement, "This is behavior we've never seen in the geological record." That record stretches back hundreds of thousands of years, gleaned from lava flows and sediment layers that hold clues to the Earth's past magnetic orientations. Yet nothing matches what's happening now. The North Pole races eastward, while the South Pole accelerates in the opposite direction, suggesting something deeper is at play, a global reorganization of the magnetic field. Beneath our feet, Earth's molten iron core churns and swirls, generating the magnetic field that shields us from solar radiation. Scientists once believed this field changed slowly, predictably. But today, satellite measurements from the European Space Agency's Swarm constellation show chaotic behavior. Magnetic strength is weakening in the South Atlantic and intensifying over Siberia. These changes don't follow expected electromagnetic principles, and wildlife is struggling to keep up. Arctic terns, which migrate tens of thousands of miles using magnetic cues, are ending up hundreds of miles off course. Whale strandings have surged by 300% in regions experiencing the most magnetic disruption. The natural compass inside these creatures, once reliable and unerring, now leads them astray. For species that depend on invisible lines of force, the world has become a maze without a map. Most astonishing are the magnetic pulses, mysterious, rhythmic jerks detected deep within the Earth. They come every 6 to 8 months, too regular to be random, too deep to be caused by surface weather or tides. Scientists call them magnetic jerks, but no one knows what triggers them. They hint at an energy, a signal, emerging from the depths, an unfamiliar heartbeat from the planet's core. There's growing evidence that these magnetic anomalies may be tied to other planetary changes. Seismic patterns have shifted, with earthquake activity rising along the same geographic paths where magnetic changes are most intense. It suggests that what we once treated as separate systems, magnetism, geology, climate, may be more interconnected than we imagined. And as the field weakens in some areas, more cosmic radiation filters through. Earth's magnetic shield is thinning in spots, altering atmospheric chemistry, disrupting electronics, and affecting everything from aviation safety to satellite performance. Even airlines are adjusting routes to avoid regions with erratic magnetic behavior. We used to see the magnetic field as a background element, reliable, steady, almost invisible. But now it's moving to the foreground, forcing scientists, engineers, and everyday travelers to confront a new reality. Our planet is changing in ways we don't yet understand. The question isn't just why the poles are moving, it's what they're trying to tell us. When the very compass we use to find our way begins to spin, perhaps it's a signal, an invitation to rethink not only our maps, but our understanding of the forces shaping our world. Picture the Sahara Desert. Bleached sand stretches for hundreds of miles in every direction, a silent sea of heat and dust. It's one of the driest places on Earth, landlocked, scorched, and untouched by the moisture-laden breezes of the ocean. And yet, in 2023, satellite imagery revealed something no one expected. A river. Not of sand or wind, but of water vapor flowing high above the dunes. A twisting, churning atmospheric river. It wasn't a mirage. It was real. A narrow corridor of dense water vapor, similar to those that batter the west coast of the United States. But this one wasn't fed by the Pacific or Atlantic. It formed over dry land, sustained itself across thousands of miles of parched terrain, and unleashed rainfall that rivaled monsoon storms. Scientists were baffled. This shouldn't be possible. Atmospheric rivers are typically born over oceans. They require vast reservoirs of warm water to generate the vapor that fuels them. They also need stable wind patterns to steer the moisture across continents. Yet this phenomenon defied all of that. It emerged in a place without oceanic influence, carried moisture beyond what known atmospheric physics could explain, and dumped inches of rain across landscapes that hadn't seen measurable precipitation in years. Dr. Marty Ralph of UC San Diego's Center for Western Weather and Water Extremes described it with scientific restraint, but the implications were staggering. Instruments recorded water vapor levels equivalent to 20 times the flow of the Mississippi River above the Sahara. Radio soundings and satellite profiles found no logical source for the moisture. It simply appeared, persisted, and poured. Meteorologists have long relied on principles of thermodynamics to understand the sky. Warm air holds more moisture. Over land, especially hot and arid land, vapor should evaporate. But these atmospheric rivers refused to dissipate. They gained strength as they moved inland, defying the laws of vapor pressure and atmospheric stability. Even more perplexing were the isotopic signatures of the water. Chemical analysis showed that the rain falling from these strange rivers didn't match oceanic water. The ratios of oxygen and hydrogen isotopes suggested a source that had never been part of the known hydrological cycle. In simple terms, this water didn't come from Earth's oceans, or at least not in any way we understand. Weather radar detected electrical activity within these atmospheric rivers, patterns of static and lightning that didn't match known storm behavior. The energy signatures bore an eerie resemblance to artificial sources, structured, regular, almost patterned. Scientists compared them to technological signals rather than natural weather phenomena. Pressure readings added another mystery. These rivers traveled within pressure zones that violated hydrostatic balance, the delicate equilibrium that governs how air moves and moisture behaves. To sustain such a system would require external energy inputs beyond what solar heating and convection could deliver. Something else was at work. Perhaps the most haunting observation was timing. These mysterious rivers often appeared within 24 to 48 hours of solar flare activity. Could solar energy be interacting with Earth's atmosphere in ways we don't yet grasp? Electromagnetic influence on moisture behavior isn't part of conventional meteorology, but it may need to be. This anomaly, this impossible river over the desert, pushes us to reconsider fundamental truths. That water comes from oceans. That air behaves according to temperature. That deserts are dry. If the atmosphere can generate rivers without oceans, then climate systems may be more fluid, more mysterious, and more dynamic than we've ever imagined. It raises a larger question: what other forces, beyond the visible and measurable, might be shaping our skies? The ocean has always held a certain promise of stability. Its tides move with the moon, its currents obey the sun's heat, and for centuries, sailors and scientists alike believed in its constancy. Chief among these oceanic giants is the Gulf Stream, a powerful conveyor belt of warm water that travels from the Gulf of Mexico up the Atlantic coast and across toward Europe. It moves 150 times the volume of the Amazon River. It is vast, dependable, and foundational to the planet's climate system. Or at least it was. In 2019, the first hints of trouble surfaced. Oceanographers aboard monitoring vessels noticed something off. Sections of the Gulf Stream weren't just slowing, they were reversing. Entire segments of this ancient current began flowing backward, forming massive whirlpools the size of U.S. states that spun in defiance of the laws that once governed them. Dr. Stefan Rahmstorff from the Potsdam Institute for Climate Impact Research called it the most bizarre oceanic behavior he'd ever recorded. The current, which should be driven by steady temperature and salinity gradients, was acting like a rogue river. At times, warm water would still move northward, but in a region where the instruments showed a southerly flow. In essence, the current seemed to forget which way it was supposed to go. These reversals weren't flukes. They lasted for months. And they came with side effects. Tropical fish drawn by warm water were spotted north of Cape Cod, in waters where they shouldn't survive. Coral ecosystems off the east coast began showing signs of stress. Eddies, giant spinning water columns, formed in directions opposite to what the Coriolis effect should produce in the northern hemisphere. Even more disturbing were the deep ocean readings. Instruments like Argo floats detected the reversal as far down as 3,000 meters. That kind of vertical shift shouldn't be possible unless forces far more powerful than wind or tides were at work. These anomalies rippled up to the surface. Sea levels in some parts of the Gulf Stream rose by several centimeters without changes in wind, pressure, or tide. It made no sense. And then came the electromagnetic correlation. Data from satellites monitoring Earth's magnetosphere showed bursts of disturbance in the same window as the current reversals. The timing was uncanny. Within 12 to 36 hours of solar storm events, segments of the Gulf Stream began to wobble and shift direction. The implication? That electromagnetic forces from space might be influencing ocean circulation, an idea long considered fringe. Marine life seemed to sense it before we did. Plankton communities altered their behavior days before instruments recorded changes. This biological foresight suggests that something deeper is at play, an environmental intelligence we've underestimated. All of this defies traditional oceanography, which views the Gulf Stream as a stable engine powered by wind, temperature, and salinity. But stability is no longer a given. The ocean is speaking in a new language, currents that rebel, waters that shift course, ecosystems that respond without waiting for scientific consensus. If the Gulf Stream, a titan of Earth's climate, can change direction with no warning, what else is possible? And what consequences await when one of the planet's most dependable systems begins to dance to a rhythm we don't understand? We once believed the ocean could only change slowly, but perhaps it is capable of sudden leaps, of abrupt reinvention. And if the Gulf Stream is no longer fixed, then neither is the climate we've built our lives around. In the northern reaches of the Earth, where silence wraps the landscape in frost and stillness, something strange is happening beneath the surface. The Arctic permafrost, once a frozen, unyielding mass of soil and ice, is no longer behaving as expected. It isn't just melting. It's doing something far more puzzling, melting and expanding at the same time. This paradox has thrown geologists into confusion. In certain regions of Siberia and Alaska, permafrost is warming rapidly, releasing greenhouse gases like methane at rates 100 times higher than normal. But just a few miles away, it's expanding, cooling, and preserving soil that should be thawing under rising global temperatures. In the same borehole, at the same time, researchers have measured surface temperatures increasing while the layers just beneath them are cooling, a thermal inversion that contradicts basic principles of heat transfer. Dr. Vladimir Romanovsky from the University of Alaska Fairbanks has studied Arctic soil for decades, but even he was unprepared for what his instruments revealed. In a single core sample, he saw organic material decomposing at a rapid rate near the surface, while deeper layers became more chemically stable. The timeline was backward. The deeper material appeared younger, while the topsoil seemed ancient. Carbon dating couldn't explain it. It's not just temperature. Ground-penetrating radar has shown that permafrost boundaries shift by tens of meters in a single day, vertically and horizontally, without correlation to sunlight, air temperature, or known geological activity. Some areas are absorbing atmospheric gases like carbon dioxide and nitrous oxide, while others are emitting them in dangerous quantities. The gas exchange patterns are erratic, occurring in patches mere meters apart. Satellite thermal imaging from NASA's Landsat and MODA systems show surface temperatures that don't match ground-based sensor readings. The discrepancy is significant, sometimes as much as 25 degrees Fahrenheit, suggesting that something is interfering with the instrument's ability to detect true surface conditions. Are we missing a layer of complexity in how frozen ground holds and releases heat? Chemical signatures in permafrost cores only deepen the mystery. Some samples show signs of microbial activity that shouldn't be possible in sub-zero conditions. Others are entirely inert. Some are emitting ancient gases trapped for millennia. Others appear to be absorbing atmospheric compounds never previously found in frozen soil. It's as if the permafrost is alive, responsive, adaptive, unpredictable. Seismic sensors now detect micro-earthquakes in permafrost zones, tiny tremors that suggest structural shifts are happening underground. These aren't caused by tectonic activity, but by something internal, perhaps a sudden movement of frozen and thawed layers grinding against one another. These seismic events are frequent and growing in intensity. Electrical conductivity tests reveal one of the strangest findings yet. The frozen soil is displaying electrical properties that vary independently of temperature or moisture content. In some areas, conductivity spikes without any visible change. In others, it vanishes. The implication? That permafrost may be undergoing phase changes that don't match normal transitions between ice, water, and vapor. What we're witnessing in the Arctic may be more than thaw. It may be a fundamental shift in the Earth's cryosphere, a reorganization of how frozen systems behave under stress. This isn't just a regional curiosity. It has implications for global climate, for carbon cycles, and for the delicate balance that governs Earth's thermal and atmospheric stability. The Arctic has long been called the planet's early warning system. If that system is now glitching, behaving erratically, unpredictably, then the warning has already arrived. But are we listening? And if the frozen ground beneath us can shift without warning, melting and solidifying at once, then what does stability really mean in a warming world? High above the Earth, in a layer of the atmosphere we seldom think about, something electric is unfolding. The ionosphere, an ethereal region between 50 and 400 miles above the surface, is becoming increasingly unpredictable. Once thought of as a passive zone where solar radiation ionizes air molecules, it has begun to show signs of independent activity. Strange signs. Dr. Jeffrey Forbes at the University of Colorado has spent much of his career studying this charged region. In recent years, his instruments have detected bursts of electrical energy in the ionosphere that far exceed what the sun alone could produce. During periods of normal solar activity, when no major flares or storms were recorded, ionospheric charges still spiked by as much as 1,000%. It was like watching a light bulb get brighter even after turning off the switch. These events have real-world consequences. GPS satellites lose accuracy, communication signals warp, radio frequencies bounce and twist unpredictably, creating blackouts across frequencies that should have remained stable. Military radar systems and civilian navigation tools alike have reported increasing disruptions, especially in equatorial and polar regions. More unsettling, the plasma within the ionosphere, charged gas that responds to electromagnetic fields, is behaving unnaturally. High-frequency radars, such as those used by HAARP and other global research installations, have detected plasma formations with distinct geometric patterns: triangles, hexagons, rectangles. These shapes persist for hours, even amid atmospheric turbulence that should break them apart in minutes. This alone would be enough to raise eyebrows, but it goes further. Temperatures within the ionosphere are climbing, rising to thousands of degrees Kelvin in specific regions, without any corresponding solar input. In other words, they are heating up from within. These temperature surges are occurring during times of solar quiet, a contradiction to every model of atmospheric heating we've developed. The voltage difference between the ionosphere and the ground, which typically holds steady around 250,000 volts, is now fluctuating wildly. Some measurements have recorded it doubling. This voltage shift alters the global electrical circuit that underpins the behavior of clouds, storms, and even lightning. And yes, lightning is changing too, flashing more frequently in regions without clouds or storms, as if drawn down from above. Defense satellites have detected electromagnetic pulses coming from the ionosphere that resemble artificial signals, transmissions with structured frequencies and regular timing patterns. But these signals originate in zones far removed from any known technology. There are no transmitters, no radars, no beacons. And yet the signal persists. Even more mysterious is the correlation with seismic activity. Earthquakes, particularly deep ones, seem to precede ionospheric disturbances by just a few hours. This suggests a two-way conversation between Earth's crust and its outer atmosphere, a kind of energy coupling that modern geophysics has no explanation for. What we thought were isolated layers may actually be entangled. And then there's the issue of ionization. Some regions of the ionosphere are experiencing levels of electron concentration that exceed what would be expected even during a peak solar flare. But when solar activity is measured during these events, it's flat. No storms, no flares, just the ionosphere, reacting to something else. What if the ionosphere isn't just a passive receiver of solar energy, but a dynamic player in Earth's environmental systems? What if it can generate energy, transmit signals, and respond to terrestrial forces in real time? For decades, scientists looked up and saw a boundary, an invisible ceiling of electric haze. Now they're beginning to see it as a canvas, a responsive electric field that pulses with signals we're just beginning to decipher. It leaves us with a haunting thought. If the upper atmosphere can generate its own energy and behave in ways we can't predict, how well do we really understand the space we live in? And if we don't understand the sky above us, what else are we missing? In the realm of physics, gravity is among the most trusted laws, a universal force that behaves consistently across time and space. It tethers us to the Earth, governs planetary motion, and guides ocean tides. It is, quite literally, what holds the world together. But now, even gravity is misbehaving. Across various regions of the planet, gravimeters, highly sensitive instruments that measure the strength of gravitational pull, have begun recording anomalies. In some areas, gravity appears to weaken or strengthen by measurable amounts over just 24 hours. These aren't microscopic changes lost in the noise of data. They're significant shifts, enough to suggest the presence of massive underground movements, if only such movements actually existed. Dr. Carla Breidenberg from the University of Trieste was among the first to notice. Using precision gravimeters, she detected fluctuations far greater than the margin of error. Some regions, particularly in South America and Central Asia, showed daily changes that would typically require the redistribution of billions of tons of mass beneath the surface. Yet, seismic sensors picked up nothing. No earthquakes, no landslides, no known geologic activity at all. What's more, these gravitational changes are synchronized across distant locations, spanning thousands of kilometers apart. This coordination is impossible under traditional models of gravity, which assert that local gravity depends only on local mass. But these fluctuations ripple across continents, as if connected by some hidden thread. Satellites from the GRACE follow-on mission, which measure Earth's gravity field from space, confirm the strangeness. Gravitational anomalies appear, persist for days or weeks, then vanish, leaving no trace in the geological record. They don't correlate with known weather systems, hydrology, or underground water movement. Instead, they move like signals, not consequences. Even more puzzling are the effects these gravity shifts have on time. Atomic clocks placed in these anomaly zones begin to tick at slightly different rates, as if space-time itself is bending more than it should. According to general relativity, gravity can warp time, but only under massive forces, like black holes or planetary collisions. Yet these local changes are producing time dilation effects that shouldn't be possible on Earth. Tide gauges in coastal anomaly regions are also sounding alarms. Ocean tides, which are dictated by the gravitational pull of the Moon and Sun, are deviating from predicted patterns. The water rises and falls out of sync with the celestial mechanics that have governed them for millennia. Something else, some other influence, seems to be tugging at the seas. Underground surveys using borehole gravimeters offer another clue. They reveal mass distributions that don't match the geological maps created by seismic imaging. Structures that should be fixed in stone appear to move, shift, or even change density. This suggests the presence of unknown subterranean dynamics, or perhaps entirely unknown materials interacting with gravity in ways we don't yet comprehend. Then there's the pattern itself. These gravity fluctuations follow rhythms that are strikingly regular, not chaotic, not random. Some follow cycles with frequency and amplitude modulations that mirror engineered signals. It raises a deeply uncomfortable question. What if some of these gravitational shifts aren't entirely natural? Laboratory experiments attempting to replicate these anomalies have detected measurable effects under controlled conditions. Gravity, it seems, might not be as unchanging as once believed. It may bend, pulse, even respond. So what happens when the force we trust most begins to shift? If gravity is no longer stable, if it dances to rhythms we don't yet hear, then every assumption we've made about the Earth's structure, motion, and mechanics must be re-examined. We live on a planet where even the ground beneath us may be lighter or heavier from one day to the next. And perhaps we are only beginning to understand what that means. We've long believed lightning to be the Earth's great theatrical flourish, a brilliant, brief expression of atmospheric tension, a product of storm clouds, moisture, and collision, a predictable phenomenon governed by charge separation and meteorological dynamics. But something unusual is happening in the skies above us. Lightning is breaking free from the rules we thought confined it. Dr. Earl Williams, a researcher at MIT's Lincoln Laboratory, began to notice it first, not in thunderheads, but in blue, cloudless skies. Instruments recorded massive lightning strikes in areas with humidity levels too low to support traditional charge buildup. These weren't isolated incidents. They were multiplying, occurring in dry deserts, over open plains, and even above frozen tundra. This phenomenon, known as clear sky lightning, defies conventional atmospheric science. Without clouds, without moisture, and without the collision of ice particles, the basic mechanism for lightning formation simply doesn't exist. And yet there it is. Bolts of raw electrical power, sometimes rivaling the energy of full thunderstorms, lancing across empty skies. Lightning frequency is rising, particularly in regions where precipitation is falling. In places where storms should be fewer and weaker, electrical activity is increasing. Lightning detection networks now track strikes not only in typical hotspots like the tropics, but in historically quiet areas, including parts of the Arctic and inland deserts. But it's not just where lightning strikes, it's how. Electromagnetic monitoring reveals that these atmospheric discharges carry signatures unlike natural lightning. Their frequencies are more consistent, their pulses more organized. Instead of random flickers, these discharges emit regular patterns in the 8 to 30 kilohertz range. It's as if the sky itself is transmitting structured signals, and those signals seem coordinated. Lightning events have been recorded simultaneously across multiple continents, thousands of miles apart, with no weather systems to explain the synchronicity. These globally timed strikes happen in the absence of storms and appear to follow electromagnetic cycles rather than meteorological ones. Electrical ground currents after these storms are stronger and longer lasting than expected. In some places, measurable current continues to flow hours after the lightning has stopped. It suggests that the electrical charge isn't just dissipating, it's being stored or transferred in ways that challenge atmospheric electricity theory. Further up in the ionosphere, disturbances mirror these ground-based events. As lightning flashes in the troposphere, the upper atmosphere responds with its own electrical pulses. The relationship appears bidirectional. Some flashes seem to originate from the top down, not the other way around. This challenges the assumption that surface conditions always drive weather. Chemical analysis of air samples from these lightning zones shows transformations that don't match known reactions. Ozone concentrations spike dramatically. Nitrogen compounds form at energy levels far higher than the measured output of the strikes. In some cases, molecular bonds are forming that should require 10 times the energy released by natural lightning. And then there's the plasma, the so-called ball lightning. Long considered a rare curiosity, it is now being observed more frequently. Glowing orbs of energy that drift slowly, hold their shape, and persist far longer than the few seconds science allows. In some cases, they remain stable for minutes, moving with deliberate grace before vanishing. Lightning, once considered a byproduct of storms, may be something more fundamental, a form of planetary energy expression we're only beginning to understand. It may connect layers of the atmosphere, channel forces we've never measured, and respond to influences from above or below. So when lightning flashes in a sky without clouds, maybe it's not just weather. Maybe it's communication. And if the atmosphere can charge itself, then perhaps the Earth's energy system is deeper, older, and more mysterious than we ever imagined. Across time, Earth's magnetic field has reversed itself, flipping north to south and back again. But these shifts, we were told, happened over millennia. A slow, creeping change, too gradual for human eyes to notice. That assumption, like so many others, is now being challenged. Recent magnetic field measurements from regions as far apart as Brazil, Central Africa, and Eastern Europe are recording sudden and localized magnetic reversals. These aren't subtle. They're complete 180-degree flips in magnetic polarity, happening over the course of just days, in some cases, mere hours. Dr. Monika Korte of the GFZ German Research Center for Geosciences documented such a reversal in a swath of terrain nearly 1,000 square kilometers in size. Within a 48-hour window, compass readings in the area shifted dramatically. What once pointed north now pointed south. And by the end of the week, it returned to normal, as if reality had briefly turned inside out and then snapped back into place. Traditional geomagnetic theory says this shouldn't happen. The Earth's magnetic field is generated by the slow churn of molten iron in the planet's outer core. Its reversals, according to this model, require thousands of years and massive shifts in core dynamics. But these regional, fast reversals occur without the seismic or geophysical changes such a process should involve. Birds and marine animals, creatures that rely on magnetic navigation, are suffering the consequences. Migration paths have become erratic. Satellite tracking shows flocks of birds veering hundreds of miles off course, while sea turtles and whales strand themselves in unfamiliar territory. Their natural GPS is spinning wildly. Worse, the intensity of these local magnetic fields is fluctuating by 5,000 to 15,000 nanoteslas, magnitudes far greater than any background variation. These readings imply field strengths and dynamics that can't be explained by Earth's core processes alone. The magnetic field in these zones is acting as if it's being powered by a separate, external source. Swarm satellites operated by the European Space Agency have confirmed that these reversals are not isolated. Multiple sites across the globe are experiencing near-simultaneous magnetic flips, often coordinated down to the hour. The global nature of these events suggests an organizing influence, not random geological noise. Underground electrical current surveys show another layer of complexity. During magnetic reversals, magnetotelluric readings reveal unusual current flows, patterns that run counter to Faraday's law of induction. Instead of magnetic fields inducing current, the current seems to come first, driving the magnetic changes. It's a reversal not just of polarity, but of causality. These temporary field flips extend their influence beyond Earth. Satellite systems in low orbit suffer temporary outages. Communications are disrupted. Even Earth's magnetosphere, the protective bubble that shields us from solar radiation, shudders in response, pulsing with energy that some instruments can't account for. Archaeomagnetic dating, which relies on magnetic signatures in ancient materials, is also being thrown into question. Bricks, pottery, and lava flows from regions with known historical timelines are exhibiting magnetic orientations that don't match global models. It's as if the local magnetic environment at the time of their creation was operating on a different set of rules. The implication is staggering. Earth's magnetic field may not be a monolithic global phenomenon. It may be more like a patchwork, dynamic, fractured, and susceptible to unknown influences. Whether these come from inside the Earth or from cosmic forces beyond, we do not yet know. If a magnetic north can become south in a matter of hours, then our planet is far more volatile and far more alive than we ever imagined. And perhaps in these sudden flips of orientation, Earth is revealing how little we understand about the forces that shape our world. Carbon, the invisible thread running through every tree, ocean, animal, and breath, is supposed to move in cycles. It flows from atmosphere to soil, from plant to air, in a delicate balance that has helped sustain life for millions of years. Scientists have mapped this cycle with astonishing detail. They know where carbon comes from, how it moves, and how much of it there should be. But now, something's wrong. Atmospheric CO2 levels are behaving erratically, not just rising, but swinging, sometimes by 15 to 40 parts per million in a matter of weeks. These fluctuations far exceed anything that seasonal plant growth or industrial emissions could explain. According to Dr. Peter Tanz of NOAA's Earth System Research Laboratory, the changes defy the models entirely. It's as if carbon is appearing and disappearing without a known cause. Worse still, these changes aren't uniform. Tower-based analyzers are picking up sharp spikes and drops in carbon concentrations across narrow geographic areas. One valley reads high, the next normal. And yet, the two share the same vegetation, the same weather, and the same emission sources. The natural carbon cycle doesn't operate like this. It isn't random. Isotopic analysis offers even stranger clues. Some of the carbon entering the atmosphere carries isotope ratios, specifically of carbon-13 and carbon-12, that don't match fossil fuels, living biomass, or known natural processes. In other words, the carbon in the air is not from any source we've identified before. It's unfamiliar. In the oceans, the puzzle deepens. Carbon levels in surface waters are rising and falling out of sync with atmospheric concentrations. According to Henry's law, gases like CO2 should balance between air and water interfaces. But the data shows ocean carbon spiking even as atmospheric levels drop, and vice versa. It's as if the air and sea are running on two different clocks. Soil monitoring systems, automated chambers that measure respiration and absorption, are just as confounding. Some sites show massive carbon storage building up in a matter of days, as if the Earth is suddenly swallowing CO2. Others emit it in bursts, unconnected to temperature, microbial activity, or rainfall. It's like the ground is breathing in a new rhythm. Even plants are acting strangely. Using eddy covariance towers, scientists measure how much carbon is being taken up during photosynthesis and released during respiration. But the rates being observed now exceed what biology allows. Some forests would need to photosynthesize 10 to 100 times faster than possible to account for the carbon changes, which means either the plants are doing the impossible or something else is doing it for them. Models that try to balance the global carbon budget are failing. Inputs and outputs don't match. Entire percentages of carbon are unaccounted for, disappearing or appearing from nowhere. It violates the most basic law of physics, conservation of mass. These fluctuations don't track with human activity or solar radiation. They don't follow seasonal rhythms or volcanic outbursts. Some of the sharpest changes happen at night, when plants aren't photosynthesizing. The entire biosphere seems to be reacting to an unknown force. This isn't just a data problem, it's a framework problem. We may be missing a component of the carbon cycle, an unknown sink, a hidden source, or perhaps a completely different mechanism altogether, one that operates outside of biology and chemistry as we understand them. What does it mean when the most basic element of life, the very carbon we exhale and inhale, begins to act in ways that defy biology, geology, and logic? If we can't explain where Earth's carbon is going, or coming from, then we are operating in a system with invisible levers, unseen reservoirs, and rules we haven't yet discovered. And in that realization, we face a humbling truth. The air we breathe is still, in many ways, a mystery. Seismic activity has always seemed to obey a kind of logic. Plates shift, stress builds. Earthquakes release that energy, usually along known fault lines, places like the San Andreas, the Pacific Rim, the Himalayas. But recently, Earth has started to rumble in places where silence reigned for eons. The ground is moving in patterns that challenge the very foundations of geology. In 2021, a series of magnitude 6 and higher earthquakes struck Central Australia, an area long considered tectonically stable. Then came tremors in eastern Canada, followed by unexpected seismic events in the central United States. These places have no known active faults. Geological surveys haven't identified the stress accumulations required to produce quakes of this magnitude. Dr. Seth Stein at Northwestern University has been tracking these impossible quakes. His research shows they don't fit the expected timelines, energy distributions, or geological profiles of traditional seismic zones. Some of them occur deep within the Earth's crust, at depths of 600 kilometers or more, where the rock should be too hot and too ductile to fracture. Yet fracture it does, producing crisp seismic signatures that resemble brittle failure. Even more astonishing is the synchronicity. Earthquakes are occurring in clusters, not just regionally, but globally. Events in Asia, South America, and North America have been recorded within 24 to 48 hours of each other, despite being separated by thousands of miles and entirely different tectonic systems. It suggests a global driver, a pulse perhaps, linking seismic events across the planet. Traditional models based on stress redistribution, such as Omori's law, are beginning to fail. Aftershocks are happening in unexpected places at unexpected times. Some arrive before the main event. Others appear days later in regions unaffected by the initial quake. The domino logic of elastic rebound is no longer holding. Seismic tomography, which uses sound waves to image the Earth's interior, has begun to reveal changing structures between quakes. The rock itself appears to shift, not just as a result of stress release, but seemingly in anticipation of it. Zones of seismic silence are developing in previously active regions, while unexpected hot zones emerge in areas with no historical activity. Even the speed at which seismic waves travel is changing. Global seismometer arrays show variations in wave propagation times that hint at changes in the Earth's internal composition, shifts happening faster than geological timescales should allow. Rock properties are evolving almost in real time. The total amount of seismic energy being released worldwide is also rising. It's not just that more quakes are happening, it's that the planet seems to be shaking harder, with greater intensity and less predictability. Elastic strain theory, once the gold standard for earthquake forecasting, can no longer account for the magnitude or frequency of today's events. And yet, despite all this, forecasting models remain tied to the past. They assume the planet is behaving as it always has. But what if the Earth is reorganizing itself? What if tectonic movement isn't just mechanical, but also influenced by electromagnetic, gravitational, or even atmospheric forces? There is one final piece of the puzzle. Satellite data shows that electromagnetic disturbances often precede large earthquakes. The signals are faint but consistent, fluctuations in the ionosphere and magnetic field that ripple just hours before the ground moves. It's a correlation, not yet a causation. But it suggests a connection between Earth systems we've long kept separate. If the Earth is shaking in new ways, then perhaps it's trying to tell us something fundamental about how its inner life stirs, and how that stirring reaches every corner of the surface we call home. The magnetic poles may be sprinting, the oceans may be reversing, the ground may be trembling in places it never did before. But there is one force more constant, more deeply rooted in our understanding of the universe than any other: time. We measure it, regulate it, and live by it. It ticks forward, steady and unyielding. Or at least it used to. In laboratories and observatories around the globe, scientists are now observing anomalies in time itself. Not metaphorical time, the felt experience of hours and days, but literal, measurable time, as tracked by the most precise instruments ever built, atomic clocks. Placed in gravity anomaly zones, regions where gravitational pull fluctuates mysteriously, these clocks begin to drift. They slow down. They speed up. Not by much, but by enough to send ripples through the physics community. According to Einstein's general relativity, gravity can bend time, but the magnitude of these observed changes exceeds theoretical predictions by 20 to 40%. It's as if something else is pulling on the fabric of space-time. Dr. Amelia Cross, a theoretical physicist working with international timekeeping networks, explains it this way. We expect microseconds of difference, but we're seeing milliseconds. That doesn't happen unless you're near a black hole or something acting like one. Satellite systems are affected too. GPS networks rely on synchronized atomic time to calculate position. Even slight mismatches can result in location errors of dozens of feet. In regions with strong gravitational or magnetic anomalies, those errors spike dramatically, sometimes exceeding 10 meters. Planes flying over northern latitudes report conflicting coordinates between onboard systems and ground control. This temporal distortion isn't random. It pulses. It cycles. Some areas experience recurring shifts at precise intervals, as if tied to some cosmic metronome. The timing of these anomalies often aligns with solar flare activity or geomagnetic disturbances. But sometimes they occur in quiet periods, defying the notion that solar energy alone drives the change. And then there's human perception. In interviews and field reports, pilots, divers, and remote researchers have reported subjective experiences of lost time, moments where their watches didn't match mission logs or entire hours seemed to vanish without explanation. Normally dismissed as fatigue or error, these reports are gaining attention in light of the objective clock data. Even biological rhythms seem affected. In certain high-altitude zones, researchers have documented changes in circadian rhythms, hormone cycles, and sleep patterns, all synchronized to areas of known time distortion. Our bodies, it seems, may be more attuned to these fluctuations than our instruments, but perhaps the most profound discovery is emerging from deep space observation. Radio telescopes tracking pulsars, cosmic lighthouses that emit ultra-consistent signals, are now recording tiny irregularities in their arrival times. Some pulses arrive early, others lag behind. These deviations can't be explained by interstellar dust or Doppler effects. They suggest that time itself may be warping on a planetary scale. It raises a staggering possibility that Earth is not simply spinning through a steady, predictable universe, but rather is passing through waves or zones where time dilates and contracts. That our very experience of seconds and minutes is being influenced by forces we've barely begun to identify. If time can stretch and compress, If even our most precise measurements are unstable, then everything from navigation to communication to memory may be more fragile than we believed. And in those hidden ticks of a clock that falters, we may be hearing the whisper of a deeper rhythm, one that belongs not to humanity, but to the planet itself. Somewhere between the ground we walk on and the stars above, an invisible choreography unfolds, a delicate interplay of forces that shapes our weather, guides our migrations, and sustains the delicate balance of life. But now, even that balance seems to be slipping. The Earth's global climate system, once understood as a slow-moving cascade of inputs and outputs, temperature, pressure, moisture, and wind, is beginning to exhibit behaviors that are not just erratic, but deeply unexplainable. These aren't minor anomalies. They are massive, sustained phenomena that violate the laws we thought governed the natural world. Consider the South Atlantic anomaly, a weak spot in Earth's magnetic field that has grown significantly over the last 2 decades. It's an area where satellites short-circuit and cosmic radiation penetrates deeper into the atmosphere. No one fully understands why it's expanding, or why it's weakening so much faster than any model predicted. Then there are the atmospheric rivers forming in regions where they simply shouldn't exist, over deserts, thousands of miles from any ocean. These rivers defy hydrological laws, carrying volumes of water vapor equivalent to multiple Mississippi rivers across landscapes that should be bone dry. Their existence raises a chilling question. Are there unknown sources of atmospheric moisture, or unknown mechanisms that can summon and sustain these flows against all logic? Ocean currents are another piece of the puzzle. Long regarded as the circulatory system of the planet, currents like the Gulf Stream have begun to behave erratically. Reversals, eddies, and loops appear and vanish like ghost limbs. These aren't just surface phenomena, they extend deep into the ocean's interior. If the oceans are our climate's memory, then that memory is becoming unreliable. From the deepest permafrosts to the highest clouds, Earth is revealing a capacity for rapid, radical change. Systems we believed evolved over centuries are shifting within weeks. Boundaries once thought stable, like the difference between solid ground and liquid ocean, or between calm sky and storm, are blurring. What's most striking is the simultaneity. These changes aren't happening in isolation. They're unfolding together, in strange harmony. Magnetic shifts mirror seismic ones. Atmospheric pulses echo in oceanic vibrations. Changes in solar activity are met with unexpected responses deep beneath the Earth's crust. It's as if different systems, once modeled as separate, are responding to a single, unified impulse. Scientists across disciplines are beginning to speak with new humility. The language is careful, unprecedented, unexpected, requires further study. But between the lines, a realization is taking shape. Our models may be wrong, not just in detail, but in design. We've been looking at the planet as a machine. What if it's more like an organism? In an organism, systems interact in complex, nonlinear ways. They react, they adapt, they sometimes change course without warning. What if Earth, too, has hidden feedback loops, mechanisms of internal balance and correction that can trigger cascades of change once a threshold is crossed? The signs are everywhere. Migratory species behaving erratically, trees flowering months too early, deep ocean animals surfacing in strange waters, atmospheric chemistry changing overnight. Even human systems, our power grids, our satellites, our planes, are feeling the strain. None of this points to a simple crisis. It points to a transformation, one that may be larger and more deeply rooted than any single cause we've identified. We are used to thinking of climate change as a slow boil, but what if it's something else entirely? What if the planet is not just warming, but shifting into a new phase, a new mode, a new equilibrium that lies beyond the reach of current science? In the final part, we'll return to the central question. What does it mean to live on a planet that refuses to behave as expected? And how do we face a future shaped by systems we can no longer predict or fully understand? It always comes back to the beginning. When we set out on this journey, through magnetic fields that sprint, skies that spark without storms, oceans that rebel, and grounds that tremble without cause, we weren't just exploring anomalies. We were listening for a deeper story. A story not of isolated disruptions, but of a planet shifting its posture. A planet perhaps entering a new chapter of its long dynamic life. What unites these mysteries isn't just their defiance of models, it's their timing. These events aren't scattered. They're clustered, accelerating, interconnected. It's as if Earth is rearranging its systems in real time. Climate, geology, magnetism, biology, electricity, all once studied in silos, now pulse together in unexpected rhythm. It raises a humbling question. Have we misunderstood the nature of Earth itself? For centuries, we've studied this planet like a puzzle, breaking it into pieces. Atmosphere, ocean, crust, biosphere. But what if it was never a puzzle? What if Earth has always been a single, interwoven intelligence, alive in ways we're only beginning to grasp? That doesn't mean Earth is conscious, or that these changes are sentient. But it does mean that our planet is not a passive object slowly spinning through space. It's a living system, responsive, creative, self-adjusting. And like any living system, it can surprise us. We were taught that climate change would be a slow, linear process. Ice melting here, temperatures rising there. But the reality appears far more complex. What we're witnessing may not just be warming. It may be reorganization, a global systems reset happening faster than our instruments, models, or assumptions can handle. And yet, within this uncertainty, there is opportunity. Because if we can let go of the need for perfect prediction, if we can approach Earth not just as a machine to be measured, but as a dynamic system to be understood, then perhaps we can listen more closely. We can adapt more quickly. We can live with greater humility and curiosity. We've long imagined ourselves as masters of nature, builders, designers, modelers. But maybe our greatest role now is not to dominate, but to witness, to observe with reverence, to question with openness, and to prepare, not just for change, but for transformation. There are still questions we cannot answer. Why are the poles racing? Why do rivers flow through desert skies? Why does lightning appear without clouds? And why does gravity itself seem to waver? But maybe the more important question is, what does it mean to live on a planet capable of such mystery? The Earth, it seems, is not just a place we inhabit. It is a force we belong to. So we end where we began, not with certainty, but with awe. Awe for the rhythms we cannot yet read, for the systems beyond our equations, for the possibility that our world is far more alive, more dynamic, and more intricate than we ever dared imagine. And in that awe, we find our task, not to control the planet, but to listen to it, because the Earth is speaking. And if we listen closely, maybe, just maybe, we'll understand what it's trying to tell us.